Okay, first we're going to do a quick review of the complex numbers. So remember that a complex number has the following form. You can write it as a plus bi. A is considered the real part, b is considered the imaginary part, and both a and b are just real numbers. So we can think of complex numbers as living in the complex plane, C, where a plus bi sits with, so a gives its x-coordinate, x is the real axis, and b gives its imaginary coordinate, y is the imaginary axis. So this looks an awful lot like R2. If we had a vector AB, it'd be sitting in the same place in R2. So why do we even bother with this real axis, imaginary axis business? Well, unlike R2, the elements of C have a natural product structure. So, and it's given by this product rule, I squared equals minus 1. So we can naturally multiply elements of this complex plane C. And we didn't have a natural way of multiplying point vectors in R2 in the same way. And how does the multiplication work? Well, a plus bi times c plus di, these are two different complex numbers. If we just expand that, if we just unpack that, we get ac plus adi plus bci plus bdi squared. So we've got a real part, an imaginary part, an imaginary part. And then this guy, is that real or imaginary? Well, remember the product rule, I squared is negative 1, so actually that's a real part in disguise. It becomes negative bd and moves over here, and this is the real part, and this is the imaginary part of my product of my two complex numbers. So we get a new complex number that way. And notice that the unit complex numbers all lie on the unit circle within C, within the complex plane. If they have unit length, they're going to lie on the unit circle. And if they lie in the unit circle, they can be written in the form cosine theta plus I sine theta. So this is an example of a unit complex number. And it's the unit complex number that intersects the x-axis with it at an angle of theta. So let's call this number cosine theta plus I theta. Let's just denote it by z for a moment. So what happens when we multiply another complex number, w, by the complex number z? Well, here's w. It's just some other complex number, not necessarily a unit. When I multiply it by z, what's going to happen? Well, we're going to get a new complex number, z times w. What is that new complex number, though? Well, it's just w rotated counterclockwise by an angle of theta. So what happens when we rotate a number by z? Well, rotation by an angle of theta is what happens. Z performs rotation by an angle of theta when we multiply it to any vector, any complex number in the complex plane. So unit complex numbers are in bijection with the rotations of R2. A rotation by theta corresponds to the unit complex number cosine theta plus I sine theta. Moreover, just like the 2x2 rotation matrices, the unit complex numbers form a group, by which I mean that rotation by theta times rotation by phi does indeed give us rotation by theta plus phi. The product is exactly what we would hope it would be. So let's just see why that's the case. Rotation by theta is given by this complex number, this unit complex number. Rotation by phi is given by this unit complex number. When we multiply them together, we get this. When we expand that out, we get 4 terms, a real term, 2 imaginary terms, and this real term in disguise. Remember, I squared is equal to negative 1. So using the product rule, we can move this over to here. It's actually negative sine theta sine phi. So we get this complex number. Now, just like before with the matrices, we can use, first we use the product rule to get there. Now, just like in the case of the matrices, we can use the angle sum formula for sine of x and cosine of x. This real part here is actually just cosine of theta plus phi by the angle sum formula for cosine. This imaginary part here is really just sine of theta plus phi by the angle sum formula for sine. So this is exactly what we would hope. It's rotation by theta plus phi. It's the unit complex number corresponding to rotation by theta plus phi. So the nice thing about using unit complex numbers to describe 2D rotations, well, there's a few nice things. We don't need to really remember any trigonometric formulas or matrix multiplication. We just have to remember this simple product rule, I squared equals minus 1. Somehow that tiny simple rule captures the geometry of 2D rotations in some way. Also, cosine of theta plus I sine theta is slightly more compact than this 2 by 2 rotation matrix. Fewer parameters, less redundancy, just 2 parameters for this one-dimensional family of rotations as opposed to 4 parameters. So that's also kind of nice. So is there an analog for 3D rotations? We saw the problems with 3D rotation matrices. Is there some analog to complex numbers that we could use for 3D matrices?